The talk will be moderated by Baron Zoka, and he is a Foundation board member, former chair, and a senior fellow at the Progress and Freedom Foundation. Baron?
And you forgot to mention, I'm also one of those lawyer varmints. So I'm not a subject matter expert, and my purpose here is really to bring you, the people who really know what they're talking about, so they can talk about the technical business and then eventually policy issues that I think might tie together to some extent the topics that we have today. So I'll just briefly introduce our panel, and then I will show you a roadmap we have for our conversation, because we really want to engage the audience as we go along, but I want you to see where we're going so you don't skip ahead of the rough outline we have. So you probably all know Bob Werb, who's our current chairman. Dennis Wingo has been a real leader in the space business, very focused, I would say perhaps more than anybody, on the immediate business realities and opportunities in the space industry. And as Dennis will always remind you, we have a $200+ billion a year space industry today, and it's ComSats and other satellites, which is actually directly relevant to our topic today. Joe Carroll is famous for having not much to say about anything, but knowing a hell of a lot about a lot of things, in particular tethers and orbital debris, and how you would actually go about mitigating and removing orbital debris. And then to my left, A.C. Trania is also a Foundation board member and has been very active for a long time on NEOs, and is, I dare say, just as focused in some ways as Dennis is on the business realities. So that's really where I wanted to start here. And if we go to the next slide, I'll show you, if you go through the slides about each of the panelists, which might have been helpful when I was introducing them. There's a slide that just kind of lays out the roadmap. So where we wanted to start before getting into substance was really about the vision here. So why it is that we should care and why this relates to the Foundation's mission. So Bob, why don't you get us started with the microphone? And I'll also remind you, if you want to ask questions as we go along, please feel free to put up your hand, but I won't call on you unless you use a mic.
First, let me say that you're probably going to get the feeling that you've walked in the middle of a conversation, and that's exactly what's happened. Over the last 18 months to 2 years, a group of about 100 people scattered around have been really thinking through the implications of what's been happening in orbital debris. And there are historic reasons why the conversation started when it started, but once it got started, it developed a life of its own. And the Space Frontier Foundation and Foundationers have been very involved in that discussion. We've been, doing papers and talking to people, and it's been very much a part of the Foundation's job to change the conversation about space. And over the last 18 months or so, we've pretty dramatically changed the conversation about orbital debris. And one of the things we've learned is that there are some similarities between orbital debris and NEOs, and there's some differences, and we're going to talk about that. The Foundation is particularly interested in this because what we want to do is to use the nearly unlimited resources of the solar system to make life better for everybody, to protect Earth's fragile biosphere, and to create a freer and more prosperous life for each future generation. I mean, that's what we're about. And so orbital debris and NEOs are both very critical to that part of our vision. And so when this discussion started, we just sort of dove in, and I think you'll find that it's a very good example of how the frontier philosophy impacts on this discussion, because the other people involved in this don't share our vision. I mean, in debris, a lot of the people concerned in the military, their interests are not in using the orbital debris. They're interested in just getting it out of the way so it doesn't cause them any problems. A lot of the people involved in the NEO discussion are scientists, and they couldn't care less if we characterize them for, in terms of their utility for a future civilization. They want to know where they came from billions of years ago. And okay, with this, and we've kind of been trying to bring all the various parts of the discussion together and to get everybody focused on how do we do this in a way that is frontier enabling, to use our term. We don't always use that term when we're talking with the rest of the community. And all of the 5 of us plus several other foundationers have been engaged in that debate and are going to stay engaged in that debate. And this is a work in progress.
And thanks, Bob. And I just want to also submit that this, to me, is a really good, this is almost like a case method in business school, except that what we're applying is really the Foundation's approach. And it's an approach that is inherently multidisciplinary. And when you look at this panel, you see a lot of technical expertise, but also a broader expertise. And that's really only a small part of what's involved in this debate. So I want to start by just having Joe and Dennis and AC really kind of lay the groundwork for us in describing what it is we're talking about. And I want to start by taking the low road on debris and then working our way up. So I want to start with Joe giving us some background about the debris threat at low Earth orbits at LEO, and then move into talking with Dennis about geostationary orbits, and then AC is going to really kind of take it home and talking about NEOs, and then we'll start to unpack the pieces here. But at each step of the way, the goal here is to talk, as Bob is saying, both about opportunity and threat, and how to make threats turn into opportunities for NewSpace and for commercial development. So, Joe, why don't you get us started on LEO?
Yeah. Orbital debris, man-made orbital debris did not exist until Russia launched the first satellite, and then battery died. Okay, then it became orbital debris. Surprisingly, the real orbital debris collision issue, you have to have 2 spacecraft in orbit at the same time. The Russian second launch, I think, occurred after the first one a decade, so they didn't cause the problem. If you look at the list of old objects in space, I think 96 out of the 100 oldest are U.S. The U.S. pioneered the use of high, long-lived orbits. So, but I don't want to blame the U.S. Every country active in space has done some things that they would later regret, okay? In 1963, we did the Project Westward. We put 480 million needles this long in high orbit. Adlai Stevenson actually argued in the UN that they would re-enter within 3 years, and most of them did, but we don't know how many are still up there, okay? But every country has done things that in later thought were, gee, I wish we hadn't done that, but we can't admit that publicly, okay? If you look at the size versus frequency distribution for near-Earth objects, it's kind of a straight line and log-log curve, very slight curvature. That's not true for debris. There are actually 3 distinct bumps, okay? The first bump is intact spacecraft. And we think of CubeSats and, you know, regional satellites, but the typical intact satellite weighs about a ton. And you could regard the intact satellites as being mostly cars. The results of explosions and collisions could be regarded as hubcaps. They tend to be under 5 pounds, but trackable. But besides the hubcaps, there's also what I call bullets, the objects that are untrackably small. They can be detected by use of the Goldstone radar, but limitations of that radar only allow you to get statistical data. They don't allow you to establish orbit. So we know that there are a lot more small bullets up there than there are hubcaps, but we can't dodge them, okay? And one of the bad stories about space station that you don't hear is that for every object that the ISS maneuvers to avoid the possibility of a collision with, there are about 50 objects which we don't track, which are large enough to put a hole in the manned module and ruin people's day.
And Joe, before you go on, could you tell us where do those small objects come from?
Largely collisions and explosions, okay? There may also be some malicious events associated, you know, byproducts of ASAT tests 30 years ago or whatever, but it's collisions and explosions. And there have been dozens of explosions. Deltas, there were a bunch of deltas, 9 of them put into high orbit back in the 60s or 70s without venting propellant tanks, and all 9 eventually blew up, okay? Up to 2 years after launch. And one could argue what they were, but you know, what attributed it, but what we know now is we always vent propellant tanks. And the U.S. has been a leader in The U.S. is a leader in vulnerability in space. So we have more assets, more target area, more dollars invested than anybody else. So we are also, very deservedly, a leader in raising people's consciousness about the things, about doing things like not leaving things in long-lived orbits. The 25-year rule is propagating over the world. Venting propellant tanks, draining batteries, all that stuff is becoming, all the easy stuff to reduce the future growth and debris is being taken by nearly all spacefaring nations.
And just so we're all on the same page in terminology, that's all broadly called mitigation.
Mitigation, that's not removal. All it does is reduce the rate at which the problem is getting worse, okay? And until February 9th or so of last year, the contribution of car-car collisions had been overlooked. It's still overlooked in some places. We worry about hubcap car collisions because there are more hubcaps. But it turns out that because car-car collisions, there's far more collision cross-sectional area, they are likely to be nearly as common as hubcap car collisions, and they're likely to involve, as with the Iridium Cosmos, 300 times more energy per unit mass than a hubcap car.
And that was the crash you just referenced that happened last year.
Right, and there are 2,500 known pieces of debris from that, approximately. But the statistical techniques indicate that the standard NASA model underestimates by at least a factor of 2 the much smaller stuff, okay? So my philosophy is if, you know, there's some techniques like ground-based pulse lasers that may be able to deal with the hubcaps, but you got to get rid of the cars. And if you get rid of the cars, you also get rid of the target area for the hubcaps. So we need to start talking about serious removal. And then there are just a few numbers. Besides the concept of cars, hubcaps, and bullets being distinct populations, another key thing is that about 73% of the mass of all the debris is Russian. And according to the Outer Space Treaty, they own it, we can't touch it. U.S. position is we will not touch it without their permission, okay? 16% is U.S. and 11 or 12% is the rest of the world put together. So it's, but the good news is if the U.S. can work out a deal with Russia, the rest of the world probably wants to get in line because we're covering 88, 89% of the problem, okay? The bad news is that we still got to work out a deal with Russia.
Okay, so that's basically the LEO situation.
Yeah.
So Dennis, why don't you tell us about what's going on at GEO, and then we'll talk about threats and opportunities in both.
Right, and we're conveniently skipping over MEO orbits, the middle Earth orbits, because that's where the radiation belts are. There's not a whole lot of assets there, and so it's much, much less of an issue. At GEO orbit, there at this time is over 270 active spacecraft, and there's probably more than double that in inactive spacecraft. I sometimes joke that the first place we're going to mine in the solar system is not a near-Earth object, but GEO orbit and the orbits around GEO, because at this time there's several 100,000 kilograms of high-value materials there. Solar panels, transponders, a lot of gold, a lot of carbon, a lot of different things that are there. And it's an immediate issue, and it has been in the news as late as yesterday. Galaxy 15, I mentioned this in the previous talk, went defunct because of the failure of the onboard processor on Orbital Sciences spacecraft, but they weren't able to turn the transponders off. Well, all of a sudden you have a several thousand kilo piece of orbital debris that's active and broadcasting. NewSpace had to delicately maneuver one of their spacecraft around, and while Intelsat takes the position that it's not their problem, the courts will probably decide otherwise should NewSpace decide to pursue the matter in the courts. The U.S. military lost a MilStar. There's about every 18 to 24 months there is an accident where an upper stage fails to deliver a satellite to GEO orbit, and a satellite is stuck in an interim orbit. And so there is a tremendous amount of hardware. And every time one of these satellites fails, it's several thousand kilos of active, like a Delta II second stage dry mass is only about 2,000 pounds. Well, there's hundreds of these, but there's also hundreds of these active and inactive spacecraft in GEO orbit. And if there was just one collision because of the nature of GEO orbit. It's a very narrow arc. It's a box is 40 kilometers by 40 kilometers by 80 kilometers in a direction. The 80-kilometer direction is going outward from the Earth. One accident of two spacecraft hitting each other in GEO orbit will knock out, has high probability of knocking out over $1 trillion of global GNP per year, because it could basically make the GEO orbit unusable.
Now, is that the entire orbit, or is that one
That's
slot?
the entire arc, because what would happen is this debris spreads out and propagates along the entire arc. And so it could literally, and it's a cascade effect, and Joe will probably talk about the cascade effect in LEO, but the cascade effect in GEO is far more dangerous because it's one orbit. In LEO, you've got all these different orbits, all these different altitudes, but in GEO, you've got one orbit that's valuable, and if you take that out, it could, and this stuff doesn't come out of the, doesn't fall out of orbit.
Air drag doesn't clean it up.
Well, so let's talk about threats. Joe, why don't you explain briefly the cascade effect problem? What is the threat? How serious is it?
Yeah, this is referred to somewhat, well, as the Kessler syndrome, okay? And Don Kessler is not particularly happy to be known to history for this, but he was the first guy that pointed it out, and it's that each object that collides with another object creates a large number of smaller objects that have enough energy because of the difference. You know, all objects at a certain altitude have nearly the same energy, but they're moving in different directions, so they can collide very energetically. If they're both in circular orbit, they can be head-on, okay? You can have a slow-motion runaway, and at certain altitudes, the rate of collisions, though very slow, I mean, one every 10 or 20 years, that's high enough that we're generating debris faster than air drag pulls it out. Okay, so we are already in a slow-motion runaway. Now, what most people worry about is this hubcaps hitting cars and making more hubcaps, all a trackable problem. I think that the major problem is cars hitting cars, which will happen nearly as often. The total mass involved is twice as much. The total energy is several hundred times as much. The pieces, on average, are going to go down to much smaller sizes. Most components of spacecraft and spent stages are plate-like. They're tank walls and circuit boards and solar arrays. And if you hit something more energetically, you can shred it into pieces that are a smaller multiple of the thickness. So you can make more bullets. And I think that, well, for example, there are 18 Zenit stages that are 8,300 kilos. They're larger than a school bus, okay? They weigh 8.3 metric tons each, and they're in a narrow altitude band between 800 and 850 kilometers, mostly between 840 and 850. If two of those hit each other or hit their payloads that were left in the same orbit, which are roughly 6-ton Selena II ocean satellites, ocean ELINT kind of satellites, they could roughly increase by a factor of 10 the number of bullets in the crowded regions in low Earth orbit.
Dennis?
Okay, that's a problem.
So Bob, what is the threat here? How bad is it? Are we talking about losing access to space completely, or just higher costs?
No. Actually, I've heard that from a number of people, that we can land up locked on Earth and you know, surrounded by debris. And that is not a realistic scenario. I mean, it's not impossible, but it's fantastically improbable. Almost any debris scenario, you could pass through the band of debris.
You just don't want to stay there for months.
Yeah, right, or even days, perhaps. But you could lose use of low Earth orbit, and low Earth orbit is immensely valuable to the military, to remote sensing, to all sorts of uses. Tourism. Yes, it basically puts an end to, you know, LEO tourism, and for manned spaceflight, it's a real problem because now you need to get up above the debris field, which puts you out of the protection of the Van Allen belts, and now you're dealing with hard radiation at MEO. It also dramatically increased the costs of operating in space because you have to, you know, quickly get through this band. It would be a real bummer, and something that all the space faring powers very much want to avoid having happen.
Let me mention one other thing, which is Dennis had mentioned several hundred tons of stuff in GEO. In LEO, the numbers are 2,500 tons, okay? Of that, 350 tons is the space station. About 300 tons is all other operational spacecraft, okay, in LEO. And the rest is debris. Broken up satellites, dead satellites, launch vehicles. Just Russian spent stages is almost 1 million kilos, almost 1,000 tons. Okay, so that's the real connection with NEOs is there something we could do with 1,000 tons of highly well-characterized, high-strength, mostly aerospace aluminum alloys? I refer to them as very near-Earth objects.
And so give us, before we turn to NEOs and AC here, give us the quick and dirty, both of you, on what we could do about these things.
Well, in GEO, since you're in an orbit, one of the nice things about GEO is that the orbital velocity, comparable orbital velocity, is much lower, 17 times lower than in low Earth orbit. It's about 3,000 kilometers an hour. And in that orbit, it makes it much easier to go from object to object. And they're all fairly close to the same orbit. There's a few hundred kilometers above and below. But it's a much more tractable issue if you want to mine those orbits, to be able to take those satellites, take them apart, re-anneal the solar arrays, reuse the transponders, melt the metals, recast the metals, do whatever you want. So there actually is an incredible resource there that's hundreds of times closer than a near-Earth object. And energetically, though, GEO orbit is more than halfway to the moon. It's in energy terms, and so if I have a whole bunch of metal and if I have a whole bunch of solar arrays and a whole bunch of stuff in GEO orbit, it's much, much easier to move that operationally to, say, lunar orbit or to a libration point or somewhere like that, to where it could actually be used in a beneficial manner.
So in a word, recycling, repurposing,
Absolutely.
reusing.
Who all saw the movie Salvage One?
Yeah, make it clear, this is in-cycling, in-orbit recycling for in-orbit use. It's not drag it back to Earth and take it to the local recycling center.
Right.
So Joe, what about the low Earth orbits?
The big challenge there is most of the things are in near-polar orbits. It's typically 70 to 74 degrees or 81 to 83 degrees. Most of the Russian is in those inclination ranges. And most other debris, including most U.S., is in sun sink, which is 96 to 100 degrees. The problem is that it's not just all nearly polar. It's nearly polar, but some of them is noon, midnight orbits, and the other is dawn, dusk orbits. And collecting that is a challenge. It turns out you can make clever use of the inclination clustering and something called differential nodal regression. If you're patient and you have a high delta V maneuvering vehicle, you can actually collect this stuff into a small number of collections. And I think that's going to be the ultimate solution. And the reason is that for diplomatic, well, the Outer Space Treaty gives absolute, strict, unlimited liability for any damage caused by a space object that re-enters and hits an aircraft or damages property or hurts people on the ground. And it's non-delegable, you can't walk away from it, okay? And it's not just the launching country, but there's a clause on collaboration that if country A launches country B's satellite from the territory of country C, all three have their fingerprints and are totally liable, okay? Now, the big challenge is if anybody wants to touch, a U.S. entity wants to touch Russian debris, the U.S. government has to agree to have U.S. fingerprints on that object. Well, nobody's going to want to re-enter it, so what really may drive an interest in recycling is the desire to avoid the liability for re-entry.
So let's unpack that a little more later, but just tell us before we move to NEOs. So you cluster these things, and then what do you do with them?
You cluster them in orbits between 500 and 700 kilometers. There's far less satellite density and debris density than between 750 and 1,000. Okay, collected in a region that's not used that much. It's above space station. It's below iridium and most other things, and if you collect it into a small number of objects that are at slightly different orbit altitudes, you eliminate the collisions between the objects that have been collected. You have to have altitude overlap. You can avoid that, but sooner or later, the launching country or country consortium has to deal with it. But by that time, it could be 30 years from now, and we know how to do, you know, enough.
So it's not a recycling, but it's a remedying.
Collection
Okay.
for immediate safety and long-term opportunity to get the creative juices flowing. That
Dennis.
also is diplomatically least difficult solution.
Yeah, one addendum, and this was an experience we had. We were going to fly as a secondary payload on the Delta II, and this still happens on the Delta IV and the Atlas Vs, is that the launch entities, ULA, Boeing, McDonnell Douglas, whoever, when they launch, they don't want to, as a company, even though there's plenty of energy on the vehicle after they release their payload, to deorbit their stage. Because if they deorbit their stage, they are responsible if it hits anything. But if God does it, if it just decays naturally, the company doesn't have any liability. The liability goes upstream to the government. So
Very
there is
brief
a
word, Joe, and then we're
policy
going to move
issue.
to NEOs.
Yeah, it's an important distinction. This is an embarrassment and company liability factor, not a U.S. government. Whether the reentry is intentional or not, the country still has strict unlimited liability.
Got it. Now, AC, you're the one person on this panel who probably won't interrupt anybody else. So I want to give you an opportunity here to paint for us the picture that these guys have painted on NEOs.
All right. Thanks, Baron. So let us tell you a story now and go a little bit beyond the neighborhoods we've talked about here. So if we imagine our neighborhood from the sun to Jupiter, we've talked about, you know about the planets, that are out in that neighborhood. You know about some of these objects that are on the Earth that are in our neighborhood. But there are some other objects in this neighborhood as well. And the rest of these objects are asteroids and occasionally comets that come within this neighborhood. So you can imagine there's a smaller piece of our neighborhood between Mars and Jupiter where probably 1 million of these objects reside that are over 1 kilometer, and even more that are even below 1 kilometer. So there's a lot of objects out there. And occasionally, through the course of the solar system's evolution, some of these objects in this belt are moved into orbits where they come by the Earth, or orbits that are very similar to the Earth's orbit around the sun. And so, as of right now, of these 1 million or so objects that are between Mars and Jupiter and that come through the Earth, we probably have categorized several 100,000 of these.
And when you say categorize?
Like through visual observation, ground-based and space-based, we have trajectory information for these objects.
And very approximate size.
Very approximate size. And so these objects we can define. How do we define these objects? Well, there's a few parameters or variables we could use. One would, some parameters include the orbital parameters that specify these objects. The diameters, based upon visual observation, we use the visual observation information to help us determine the diameter based upon certain assumptions about composition. So composition is another thing. And so depending on the size, the trajectory, the composition, these objects can be categorized in different categories. And so some objects and there's a taxonomy that you can look up and where we have defined these objects. So there's these C-type asteroids, which are a large percentage of the objects that are out there that come by the Earth that are dark, maybe have volatiles, etc. There's S-type objects, which are stony objects. And then there's some other smaller types of objects, including very metallic type of objects. Now, all these objects could have dirt, could have volatiles on board on these objects, and could have metals on board. And on the Earth, we use these metals for our society, for our economy. And what has happened is, in the Earth's history, as the Earth is formed in our solar system, these kind of metals are actually underground, and it takes a lot of effort sometimes to go deep underground and get these metals out. On these asteroids, because they are smaller and have much smaller than the Earth, these metals are much more easily accessible in some ways. And so you can think about why we would go to these other objects in the neighborhood for 3 fundamental reasons. One reason is science. The scientists want to go understand the evolution of the universe and the solar system, etc. Another, I would posit, would be defense of the planet against potential impacts that have happened in the past and may happen in the future from both large and small objects. And the third reason you would go to these objects would be for money. In terms of these metals that are available that we use as a society on Earth are available out there, and potentially could we use those for uses in space or bring them back down for uses for terrestrial industry. So now of these, so on Earth, for instance, on let's say these kind of metals, and let's say the platinum metals, including iridium and palladium and platinum, when you dig on Earth, they might be available in probably a few, 4 to 5 to 6 parts per billion as you're digging on the ground. In these objects in space, they might be in the tens of parts per billions or 1,000 parts per billion. So these objects out in space have these metals that are potentially valuable. Now, how valuable are some of these metals that we use on Earth? Platinum, for instance, is trading currently around $1,500 an ounce or so. Might go up next year a little bit in 2011. So that's tens of thousands of dollars per kilogram, in essence, for these metals. Now, to give you a rough estimate, sample return missions from NASA and other countries, both in terms of missions that have gone out and missions under proposal and concept design, there is a potential mission to do a sample return that would be maybe a $400 to $650 million mission from NASA, and may return 2 kilograms, right? So that's a lot of money for 1 kilogram, hundreds of millions of dollars per kilogram if you don't include the science revenue, for instance. So the idea would be that we currently are going to these things for science, but there are probably other applications for going to these objects, such as defense, planetary defense, and also in addition, the reason for money for commercial purposes, to harvest the resources that are out there for in-space use and for use back on the ground.
So Bob, why
Can
don't
I
you
break in one more thing? The reason we know about the platinum group metal concentrations is meteorites, which are broken off pieces of these, and we look at the statistics, and they are richer in platinum than platinum ores that we're mining. The other thing is a word to remember, Sudbury. It's the world's largest nickel mine, and it's an asteroid. We're doing asteroid mining, but only after it hit, and that really joins the threat and the promise.
So Bob, why don't you kind of tell us here about the big picture? Well, how much is this stuff worth? Has anybody written any books on mining the sky that we should read? And then also, what are the applications for those metals? Sure, they're valuable, but how does it change Earth, as you were saying about the Foundation's mission?
So I'm supposed to channel John Lewis here. They're immensely valuable. I mean, leaving aside the fantasy of the $1 trillion asteroid, where you multiply the amount of metals on the asteroid by the current price, which is silly. It's absurd. There's not that much demand for these metals. We don't use them in large quantities. But they, particularly for use in space, for moving our, for the economic development of the solar system, if you will, these are the resources, the physical resources that we need to build solar power satellites, to build colonies in space, to build anything that we want to build that is of any significant scale. We will clearly never be able to launch things by the trillions of tons into space, but there is trillions of tons worth of usable stuff in space, and we can go use it. And of course, if you like, you could read John Lewis's books, who has written about this extensively. So
if the Foundation is all about an expanding human civilization in space, it sounds like you're saying this is essentially the raw material that is the essential ingredient for that to happen.
As well as the moon. The moon is the other relatively low delta V source of these sorts of materials.
And my book, Moonrush.
Oh, yes, and your book, Moonrush.
Which is about mining, just as Joe was saying, mining largely asteroid impact sites on the moon.
Correct.
So I hope that paints the big picture here, but I want to talk just briefly before we get to compare and contrast about what exactly is the opportunity. We've talked about this in the aggregate, in the big picture, but on a practical level, what does a business that is oriented towards trying to use these resources actually look like? What are they going after? And then how does it relate in particular to the threat? So we haven't talked much about this, but of course any one of these near-Earth objects could cause us all to have a rather bad day. So are these capabilities related of actually going out and mining versus doing something about a threat, AC?
Yes, I would say probably. In terms of if you were to go about to mine something like this or to attempt such a mission, before you'd actually go with your equipment or robotic spacecraft, you'd have to do surveying, assessments. Just as if you were attempting to change the course of an asteroid so that it would not hit the Earth, you would have to do similar assessments, characterization of the target, reconnaissance. So that reconnaissance would help both in terms of science, defense, and the commercial potential of exploring these bodies. And those kind of activities, reconnaissance activities, for instance, could be done by the government, but have synergistic value for the public in terms of defense and science, but then also for commercial industry, in terms of once commercial industry uses that data.
So I want to unpack that point later, but tell us, okay, so let's assume that someone's figured out the characterization problem. Roughly, quickly, what does a mission look like?
I think it depends what is the end state of the material. Is the end state bringing it back down to Earth? Is the end state using it somewhere else and bring it to LEO or GEO or somewhere else? So I think you'd send a reconnaissance mission, then you would send some kind of spacecraft. My own personal view would be it would be a robotic spacecraft and potentially not a human-tended spacecraft, because these mining operations could be very hazardous operations, and would like to be automated in the sense of when we are dealing with situations at wells at the bottoms of our oceans, we are sending robotic spacecraft down there, multiple robotic spacecraft for redundancy, et cetera. So there are multiple techniques you could use to extract these materials, drilling, melting, kind of other kind of methods. So there are probably, once again, depending on the information from the reconnaissance, that would inform the type of drilling activity or mining activity that you would potentially do. But I personally think, and I don't want to poo-poo a lot of things, a serious end-to-end analysis is probably needed. But I think legitimate large-scale mining is not something in the tens of millions of dollars. It's the hundreds of millions, billions of dollars. Especially, and I would be very concerned about the last mile or last 100-mile problem, in essence, of bringing that stuff back down to Earth. In terms of there's a lot of legal, policy, technical issues related to that.
So let's unpack some of those as we start talking about commonalities and differences here. But before we do, I just want to again remind you that we're happy to take questions if you have one on background before we get into comparisons and contrast, please. Al, and could we use a mic here, because I won't call on you unless you have a mic in your hand.
Al Globus, San Jose State at Ames. I've been told, and I think it was a good source, that there are about 10,000 dead satellites in orbit around the Earth. Is that about the right number?
To my knowledge, there are
Joe.
about 2,562 objects over 2 kilograms, totaling 2,166 tons, excluding ISS. And I exclude that because it's the only one that reliably maneuvers to dodge the other stuff. And it's the only one which is likely to still be an active satellite by the time we're going up and clearing out the rest. Everything else that's active is probably going to be debris by the time we're collecting it 5 or 10 years from now, if we can do that, okay? But excluding ISS, it's 2,562 objects over. Now, that's before the Iridium Cosmos collision. That was Nick Johnson's database right before that. And again, totaling 2,166 tons.
So quite a bit less than 10,000.
Yeah. Now, excuse me. If you want to say the number of tracked objects, okay, the regularly tracked objects, that is about 10,000, because they're about, there's 3 or 4 hubcaps per satellite per car. Okay, it's one of the
Generally
convenient
4
things. Yeah, generally 4, but
in my experience,
cars.
So a couple thousand satellites and 10,000 objects.
Yeah, 10,000 fragments. Okay, and by the way, the fragments includes CubeSats because they're under the 2 kilo. There's a bunch of stuff under 2 kilos and a bunch of stuff over, and very little between 2 and 25 kilos.
So Dennis, tell us about the technical similarities here. Are there meaningful similarities between the technologies for dealing with debris versus going after NEOs?
Well, it's in 3 parts. In one, for low Earth orbit, I will always defer to Joe because he and I have been of the same opinion for over 20 years now. Electrodynamic tether is really the only way to do a low Earth orbit. But electrodynamic tether is not worth a hoot over about 3,000, 5,000 kilometers. So fundamentally different technologies are used for geo orbit. The nice thing about geo orbit is that the delta V's between objects is low. But the capability that you develop for operating ubiquitously in geo orbit to do this type of action is also 100% applicable for near Earth objects. Maneuvering high delta V to get up there because it takes more energy to get from low Earth orbit to geo orbit than it takes to get from geo orbit basically to Mars in terms of delta V. So the same type of system can be used for both of those environments that is completely inappropriate for a low environment, but you have one, you get the other one for free.
So that's the technology of actually doing something with the object. But AC, you started talking earlier about a more fundamental technology of tracking and characterizing these objects. So how similar is that capability for debris versus NEOs?
I think there's probably a few answers to that. One is both the tracking aspect of it, this database of objects that are close to the Earth or away from the Earth, and there are various military assets that are used to track these objects near the Earth, and some civilian assets. There are also, similarly on the NEO side, some military assets, and also some civilian assets that are used globally to track these near-Earth objects. So I think there's some similarity there at some fundamental level, but I think the actual assets that could be used might be slightly different. There has been some talk that on the NEO issue, for instance, what would really be helpful would be a space-based, dedicated infrared system a little bit away from the Earth to really find a lot of these objects, these near-Earth objects, so we can see their infrared signature versus the background. So that might be a slightly different asset required for NEOs versus the orbital debris situation. There is the issue that some of the assets that will be used for both of these things would be owned by the military or are owned by the military, and so both in terms of telescopes and other things. So there is some commonality there.
So let's segue then from the technical to the policy and start talking about what this actually looks like. Who's going to do the tracking? And who should? So you said the reality is that the government, the military, is already tracking these objects in orbital debris because, as was mentioned earlier, they have a strong incentive to protect their own assets.
Yeah, let me just mention that the primary tracking mechanism in low Earth orbit is radar. In GEO and for NEOs, it's optical. And there's a Russian investigator by the name of Agapov who, there's a big meeting at the AMOS conference, the Air Force Maui Optical Site has a big user conference. They've got world-class adaptive optics, but it's open, and there are Russian investigators. This guy, Agapov, runs a network of observatories, Russian observatories, that are tasked out on a commercial basis to keep track of what's up there in GEO. So there's more overlap between GEOs and NEOs than between LEOs and.
So, of course, at the end of the day, the people in Washington don't really much care about the technical details, right? Yeah. So the question is, does a policy approach to dealing with both problems, are they going to look similar? Is one going to set a precedent for the other? And can these things really be separated at all? Or will people in Washington, rightly or wrongly, think of them as being really along a continuum of the same sort of concern, both as threats and maybe potentially as opportunities?
Depends on what happens in the court case between NewSpace and Intelsat. Because this is an orbital debris event, if you're using a definition, and one company has harmed another company. Right now, it'll probably be fought out between the underwriters, the insurance companies, and the companies themselves, but that will set a precedent. And as you know, as an attorney, precedents are important on this action. And if Intelsat ends up being found at fault, or if the insurance companies end up being liable for the loss, they're going to push to have the laws, and they've got a lot more money than we do.
To have the laws what?
To have the laws changed to better affix liability. And when liability is fixed, like right now Intelsat says, and they're basically right, as in under their policy, after the satellite is no longer controllable, they're not responsible anymore. But that's kind of a cop-out, and it will be figured out in the courts if they do have long-term liability. If there's on-orbit servicing systems in place in GEO, again, business-wise, that helps tip the liability scales in a different direction than if we don't have any capability, but that same capability is then able to be used for the NEOs.
Bob?
Yeah, to put that in more general terms, one of the reasons that we are, the foundation and the people on the stage here are so interested in the policy implications of what's happening with the debris problem is that if we can create precedent on how we treat these objects that we need to deal with in the next 5 or 10 years, because the debris problem, if you wait much longer, it just gets out of control. And if we can create the right sorts of precedents, those precedents will carry over to mining the asteroids. And we've been advocating a law of the sea sort of approach, which you can probably explain better than anyone else up here, but where you have rights of salvage, you can own things by pretty much just grabbing them. And I'm simplifying, of course, but and there's been some worry over the years that the legal impediments to mining and using the asteroids could be the big problem. When we have the technology to mine them, we may not have a legal environment where we can mine them. If we can create the right legal model in dealing with the orbital debris, it becomes much easier down the road.
I may be naive. Could you use the mic, please?
This whole aspect about the legal issues of mining kind of strikes me because several generations ago, there's a little island nation that had no natural resources, and it attacked Manchurian China for iron ore, a pretty big guy. Back then, they weren't what they are now. And the United States was China's kind of protector. See, the United States started amassing a fleet out near Hawaii as an attack force. The British fleet joined us. This little island nation that attacked China because they had nothing of their own, then attacked Pearl Harbor. They didn't care. When you don't have the natural resources and you need them, I say the laws go away. And what was it, a month and a half ago, Japan made their return, landed in the outback. That country has now started growing gold and platinum, and I hear the thing all the time, it won't do it, it'll destabilize the entire world economy. No one will ever do that. No little country would attack the United States and British fleet at Pearl Harbor. Same country. They still don't have the, I just say, people always say, oh, the legal aspect. When someone's hungry and they need that platinum for their economic base that they didn't even have back then, for the technological exports, I really think that whole thing of, legal this, I think a hungry country that did it before, and I respect them for what they did. But if you're hungry and you need it, and here's a way that you can do it without civilian casualties and being subject to atomic retaliation,
legal cynicism.
I really think that it's going to happen.
Let me channel Jim Dunson here, who was going to be on this panel but couldn't join us. The problem, as I see it, is not that there's this raging demand for something that is being restrained or held back by the law. Because if that were the case, I think the scenario you describe is inevitably at some point what happens. I think by contrast, the situation here is instead one in which the legal regime is holding things back in a much different way. It's that there is all this initial uncertainty that is so far back in terms of the production process of investing in technologies and even doing the groundwork of categorizing, characterizing, tracking objects, that you're never going to get to the point where you could just reach out and grab something. So to put it in very simple terms, you describe reaching out and grabbing something. Here what has to happen is building up a technological, complex system, and really an ecosystem for taking advantage of these assets. And I think that's the kind of thing that actually is retarded by the law, and particularly by the law in inherently international environments, where change ultimately has to come from some sort of international agreement.
However, they have already proven that they've gone.
Okay. Well, let me give you a little more meat on the bones here about what we mean when we talk about these legal issues. So one is the liability issue that Joe and Dennis have touched on, right? And that's something that could potentially drive changes in the industry itself. Could also drive the insurance side of the industry to support some sort of a pool, and this is something that Jim Dunstan and Bob Werb have developed for dealing with orbital debris, where you could easily imagine that the fees that are paid in by satellite operators every year, they don't really go to the FCC, because the FCC really spends only a fraction of those fees in regulating the satellite industry. But those funds could go into a pool that then pays out bounties for taking out a certain number of objects. So that's one way in which you could, as a practical matter, start to deal with liability issues. But then there's the question of salvage rights. So that's what Bob really had in mind when he said that we need to look to maritime analogies. This is something Jim Dunstan has developed, I think, uniquely, and could speak to better if he were here. But then there is the broader issue about property rights. And the fundamental question is, what does it mean to appropriate property in space? And without turning this into a space law panel, I would simply say that the quick and dirty version is that the Outer Space Treaty says you cannot appropriate territory.
National sovereignty can't be established.
Let's not tease out the differences. Let me simply say that in 1979, when the Law of the Sea Treaty, which was essentially similar to the Moon Treaty, which was a step beyond the Law of the Sea Treaty, was moving forward, the Carter administration, and John Breaux in particular in the Senate, put forward an approach to dealing with that problem, which was basically to say that the United States would enact a provisional licensing regime and would encourage other countries to do the same, and then recognize their respective laws to grant exclusive claims to mine a particular area of the seabed floor, without appropriating territory or claiming national sovereignty over them. So that's one model that could potentially be used for mining claims. So if you, for example, so Joe, I think it was you who suggested the idea of, well, what if somebody could be incented to place transponders on a particular object, which would, of course, give us the better ability to track them, to figure out where they're going. That could
Not
be
just that, but to predict further into the future whether we have to nudge them.
Precisely.
And that gives you more lead time, so you don't have to push them as hard if you do have to nudge them.
So the point here is not to exhaust this, but to simply paint a picture of the kinds of things that could be done. So that, for example, one could imagine a similar law, just like the Deep Seabed Hard Mineral Resources Act, that establishes an exclusive licensing claim system for an asteroid. So that if you do the work of actually tracking and characterizing a particular object, you could have property rights in that. So then we get into more difficult questions about how small something or how big something has to be before it crosses the line into a celestial body like the moon, which clearly can't be appropriated. But again, that's a space law panel. Mike Mealing.
This actually brings up one of the questions that I've had for a commercial NEA mission that's been sitting in the back of my head that I've actually bugged AC about a little bit. Most of the NEA missions have been about going
That's
to
a near-Earth asteroid.
Yeah, not an object, but specifically an asteroid. Instead of going to something big, trying to find something small, something on the size of that couch. And instead of taking all the scientific instruments and everything, studying it there, the only thing you do is send out a vehicle big enough to be able to bring it back. Dock it with the ISS and study it there. Do I actually have the ability to say I have exclusive rights to grant research access to that body? That's the problem. Because if I bring that back and somebody's able to sue me in court, in international court somewhere, and say it's a celestial body, you don't have those rights, there goes my business.
And I'll simply say that, one, that's exactly the point that Bob was making about the precedents here that are set being the ones that will fundamentally determine space law in the future. Because what really matters is not necessarily what the treaties say, but what claims you have in exactly this sort of a scenario.
Right.
And there are precedents already, of course, with moon rocks that were brought back by the U.S. and the Soviet Union, which have been granted and transferred and even sold. So a legal argument could be made that you would have a right to that object. But this is what we mean by saying that there are fundamental similarities here that will be established in dealing both with debris and with NEOs or NEAs that are going to guide development of these objects in the future. Anyone on the panel, or shall I take another question? This gentleman in the center here. And could you identify yourself?
I was thinking that isn't there a good point in terms of liability? It can work for us in either way. If a company declares that they are liable for this satellite, they own it, or rather the court decides that they own it.
The country has to agree to that.
Well, I was saying, given that a court says, okay, you company are liable for your satellite even though you're no longer in control of it, that's a stimulation and an incentive rather to get that satellite under control so it isn't going to cause harm. And if a court says, no, you're not responsible for it, then that's essentially saying that the satellite is no longer their property and then is
So Dennis, is that basically the point
to,
you were making?
Yeah, but it's actually a little bit easier than that. The insurance underwriters wield enormous influence. All they have to say is, well, okay, it's not in the contract for you to do it this time, but, next time you come to us for insurance, your rate's going to go up about 6 points. That encourages cooperation. And there are ways to do this extrajudicially within the community. And that's really because right now you're not seeing the behind-the-scenes discussions going on. And it's been my experience that they try their damnedest to keep this out of the court, so it'll probably be settled extrajudicially unless somebody just wants to be intransigent, and then it'll get to the courts and it'll be settled.
And Dennis, before I turn to Bob, let's just keep in mind that is how most things work in the real world. This is why most people install fire extinguishers in their house or sprinkler systems. It's not because of a regulation, it's because their insurance company gives them a discount. And the same is true for safety features in cars. Bob?
I want to emphasize that the vast majority of objects in low Earth orbit that are risky and could cause problems are not owned by any company. The vast majority result from the military of the Soviet Union. Now, the Russians sort of have responsibility for that. He tends to say just Russian, but I think there's a real distinction between the new debris being created by Russia and the old debris that was created by the Soviet Union, which is the majority of the threatening stuff. So in terms of the threat, we've got to make a deal with Russia. Because, they're not going to be, if we just go up and start grabbing their stuff, they're not going to be happy.
Yeah, and the Russians with the Cosmos Iridium collision, theoretically, under the law, the Russians were responsible, but all the Russians had to do, and this is what they said, is that, well, it wasn't our problem. Iridium maneuvered itself into the path of our defunct satellite. We had nothing to do with it. It's all Iridium's fault.
And to emphasize something that was said already that I kind of blew by a little quickly, countries have total liability for things that re-enter, but the liability for things that hit each other in space is vague at best.
It's for fault. And I don't know what the legal interpretations are, but my guess is that if you follow industry practice successfully and there's a collision, you're home free. God did it. I think we blame far too much on God that we could take responsibility for, but that's the current, you're liable for fault in orbit and absolute strict unlimited liability on the ground.
AC, before we leave this point, how does this relate to NEOs? What sort of a disincentive is there now against bringing something back because it creates either legal liability if it crashes on the Earth's surface or hits someone, or at least the political perception that there's a lot of risk involved?
I think if you're looking at a purely commercial mission, as a commercial venture, I am looking at this mission versus alternative investment opportunities terrestrially. So the alternative investment opportunity has a lower parts per billion in terms of composition of platinum metals, but it's a much less riskier venture. It may be comparable in terms of actual dollar amounts perhaps, but it is in terms of actually overall risk is very low. And so when I go into space commercially, I want to have as an investor, I want to have a low. I want to know what are the laws. Now
You want certainty.
The laws, yes. So now whether they're bad for me or good for me, I will decide that. But I'd like to know what they are. What is the playing field? If I'm an investor, I want to reduce the overall uncertainty in my investment to understand whether. Do I own the property if I do bring it back to LEO, or if I bring it back to the Earth's surface, and if I do want to bring it back to the Earth's surface, what are the E sub C calculations I have to be able to prove to the FAA AST or to the United States government in terms of this object re-entering? Where is it going to impact? Those kind of things. So
that sounds like one hell of a re-entry license.
Yes. I mean,
or entry,
yes.
I should say. Would not be re-entry.
Yes, I think they'd be very concerned about that large of an object potentially you may be bringing.
Jeff Faust.
Yeah, I want to tie this into something we were talking about this morning. That's LCRAS, low cost, reliable access to space. If we really do dramatically reduce the cost of access to space, A, does this close the business case for some sort of orbital debris remediation technologies, or B, does it potentially disrupt those models for recycling, reusing those materials up there, because it turns out it ends up being cheaper in the long run simply to launch stuff from Earth than trying to recycle stuff in orbit?
There will be more people putting more stuff up, and they will be people who, just like the current people, have just enough money to do what they want to do, and they don't have a budget or a need or legal requirement to remove it when they're done. Okay? So the collision rates vary with the square of the density. The density's been going up more or less linearly, not exponentially. And that will accentuate, that will make more urgent the need for going beyond mitigation into active removal.
Dennis, does it make it easier for your business to actually get running?
Well, you're talking geo, and I make this point often, is if launch was free, it would only reduce my cost by 20%. If I reduce the cost of my spacecraft by 50%, I reduce my system cost by 40%. So launch costs are not the driver for the higher orbits. They definitely are for the lower orbits.
And what is the cost? Because we had a question here from the internet that basically asked, what's being developed now, and how much would it take to actually bring it to fruition apart from launch? So that's basically what you're describing. What else but launch are the gating items?
Well, right now, the gating item is the private capital community and our other work. But it's just basically doing it because we already have the design. We already have a design that's already been accepted by the customer for a geo mission, and so there are no barriers. There are no it's just working with the private capital business. And when we have the first system in orbit, then we're golden. Then we have complete operational capability, and because our system is intrinsically high delta V, we can do AC's missions as just the next step.
Thing.
Just want to have a comment. I was doing actually work on the shadow MMOD risk model and actually quantify the risk. What I want to say is MMOD risk is single most threat to what we're talking about, the human expansion to space or commercialization, because the threats, the risk is really alarming. What I want to say is that any single approach is not going to work. We have to rely on multiple approach, like an insurance approach alone will not work. We have to rely on international trade in the first place, because when I was at NASA Goddard, we already have a NASA requirement that before you even launch, you have to, we call it something design for demise system. We want to make sure before you launch, you have a control, a controlled return. So one aspect is international trade. Another one is we have to create an incentivize the market. So to encourage the commercial approach to try to go there and actually make profit to collecting and solve those problems. Another one is insurance, of course, is one of the legs. You have to use sort of multiple approach.
I want to take one more question from Wendell and then ask Bob to wrap us up.
Given all the discussion of insurance companies and so on, I'm a little surprised nobody's brought up AsiaSat, which was a satellite that was stranded in a geostationary transfer orbit by the failure of the final stage of a proton, had an apogee at geostationary, perigee, and low Earth orbit. It was written off as a total loss, and the insurance company owned it. Hughes Aircraft bought the satellite from them, and using only the stationary thrusters on it, raised the orbit into what's called the fuzzy boundary region of the Earth-Moon system, put it around the Moon twice, and then lowered it into an orbit that was approximately geostationary from which they could deliver services for a few years and make some money. So this kind of activity of transferring assets, moving them around, and relocating them for other purposes has already occurred.
Yeah, but Wendell, at this time, we had another issue with one of these, it was AMC 14. Could have done the same thing. The industry has become more conservative since 1998. And again, the reason Hughes was able to do that is that they were willing to write a check and they saw that they could make a big profit. I actually think the capital industry today, because of the dot-com era, because of the internet era, they saw their ability to make big bucks in these other areas and not in space. Hopefully now with all of the debacles and there's a lot of money sitting on the side, that we may be able to re-entice some of the capital people back into the market, because again, if we'd had $5 million a couple of years ago, I could have turned that into $200 million in 6 months. But again, where's the buck?
So before Bob finishes up here, I want to ask you that this really raises what I think perhaps is the most important question here, which is how do we go about reducing the giggle factor on both of these things? And I mean that for investors as well as for policymakers. So why don't we start with Joe? Final words on giggle factor?
Yeah. EDI is electrodynamic debris eliminator. We think it's the way to deal with orbital debris. And there is a precursor to that called TEPSI, which I'm working with the Naval Research Lab on. And that may fly late next year, and that will answer a bunch of questions. And then NRL is interested in working with us on what we call mini EDI. And after those two, we will have a good idea as to whether there should be no giggle factor left by then, okay, for wholesale orbital debris collection, okay? It has nothing to do with NEOs, but it will probably generate more magazine article space on NEOs than it does on LEO.
So if you build it, they will come.
I think there's a serious possibility.
Bob? Dennis?
You know, where's the check? But again, a lot of people, and I want to emphasize this point, because you hear a lot of people, you hear them here today, you've heard them in this session say, well, we need the government to incentivize this, we need the government to incentivize that. For what we're doing in geo orbit, I don't need any of that. We need a check.
AC?
The government will need to incentivize, no. So on the NEO side, I think what is helpful is information. Information leads to knowledge, hopefully. So in the sense of new information or more information about these objects, like I said, on the small scale of those under 1 kilometer being potentially those objects and larger that may destroy the Earth or have global-wide consequences. For the small ones, I think we need to have more information, and thus the NASA Near-Earth Object Office is funded at about $4 million a year. So that's the official NASA line item for tracking NEOs. The new NASA budget, if it passes, might increase that 4 times to $16 million a year, so that'd be good. So we will have more money for observational data. And also there are some new telescopes, ground-based telescopes coming online, Pan-STARRS, the first telescope of which is operational, and this other one a few years called LSST. And what that will do is actually we will be getting a lot more information on these near-Earth objects, the smaller ones that are very close to the Earth. So I would anticipate over the next 20 years, as these telescopes come online and more information comes available, we will have occasional, every few months, massive media stories of objects that will have very high threat levels, and that will be happening over the next 20 years that I would forecast.
And do you think the media stories about Joe's technology or Dennis's technology working for orbital debris will help to reduce the giggle factor, help get funding for tracking NEOs, and help drive investment in your area?
Perhaps there are different technologies and different missions, and I think the fundamentally, if I just think about it now, what will be most helpful is this idea of the legal regime, policy regime, which I think on the commercial side will help define this neo-legal policy regime. There's also, in terms of reduction of the giggle factor, the new NASA plan to go back to a NEO with humans by the mid-2020s is helpful. But beyond that, what's also helpful is in the Exploration Systems Mission Directorate, there's an emphasis on new robotic missions to near-Earth objects on both the $100 million, $200 million level, and $500 million level, to have a campaign and a series, sorties of missions to NEOs, which I think will be helpful in order to get more information about various objects in the future.
So Bob, just take us home. What is the Foundation doing about this? And for people who are interested, how can they get involved?
We kind of started talking about the very big picture about creating a spacefaring civilization and why all this is so important to creating a spacefaring civilization. So I want to end with the most near-term problem, which is the LEO debris problem, the high inclination, to be specific, the high inclination NEO debris problem. And how do we use that problem to, well, not use that problem, solve that problem in a way that creates a substantial market for the NewSpace community and allows us to bootstrap and move on to bigger and better things that we want to do down the road. And what Jim Dunstan and I first conceived last year and proposed to DARPA and in other venues is that we do this by government doing its job and letting the private sector do its job. Basically, government's job is to set the rules by which the rest of us play the game. Not to play the game, but just set the rules. And one way to do that in this case is to both disincentivize people to create new debris and incentivize people who can mitigate or remove debris is to have a fund. And people pay into the fund when they increase risk by whatever they, if they do any kind of action that increase the risk of a debris cascade, then they have to pay into the fund proportionate to the risk. And Joe's done some work on how you actually quantify that and turn it into dollar numbers. And then the money in the fund is then used to pay people who help make the problem less. There are other models. The carbon trading is another model, which we actually, this was one that we started with, and we actually became convinced that it wasn't as good a model, but it's certainly better than what everybody's knee-jerk reaction was 2 years ago, is that what we need is cost-plus contracts and lots of new technology. We do not need cost-plus contracts and lots of new technology. We need government to do its job and then get out of the way.
Well, thank you all. I hope that you'll walk away from this with a better understanding of these two topics, maybe of how they fit together, and also on the last point that Bob mentioned, if you're interested in this, I encourage you to check out the presentation that he and Dunstan did. Jim Dunstan and I also did a very short piece on this in Forbes, and this is getting more attention. So I hope that this is the beginning of a positive cascade effect of drawing attention to this subject, and that it goes from orbital debris into NEOs, and that even though these things are quite different in some ways, that it does attract at least attention among policymakers and the media. And Joe has to have the final word.
Yeah.
One word.
The kind of metal processing you might want to do in vacuum with solar energy or in zero-G may be quite different from metal rolling, ingot metallurgy. If you want to do some web searching, I would say the Osprey metal process and its terrestrial markets, there is some relevance. It's worth looking at. Okay, it's only one. There's also direct metal vapor deposition, but there are many techniques that could make large structures that have better properties than available by conventional metal ingot metallurgy. Okay, so it's not just a matter of making do with scraps. You can actually get better properties than you can with conventional techniques.
Could you spell Osprey?
Osprey, it's O-S-P-R-E-Y, I believe. It's a British company. It's not named after the bird, but it's a metal spray deposition process. It's used in Mercedes-Benz cylinder liners, among other things.
Got it. Thanks, Joe. And thank you all. I think Bert, actually, I should let Burton say one thing here because I think I know what he's going to say. But if you could just give him a mic.
Yes, thank you. For those of you who weren't here yesterday, just a heads up on the orbital debris side, the European Commission has now come forward with a new funding program for orbital debris research. We held a workshop this past Wednesday at Stanford. Anyone who's interested in learning more about this can come speak to me. Thank you.
Right. So the lesson from the panel is that government should do less meddling and allow us to use that metal on our own. Right. Thank you.
In the manned module and ruin people's day.
And Joe, before you go on, could you tell us where do those small objects come from?
Largely collisions and explosions. Okay. There may also be some malicious events associated, byproducts of ASAT tests 30 years ago or whatever, but it's collisions and explosions. And there have been dozens of explosions. Deltas, there were a bunch of deltas, 9 of them put into high orbit back in the 60s or 70s without venting propellant tanks, and all 9 eventually blew up, okay, up to 2 years after launch. And one could argue what they were, but what attributed it, but what we know now is we always vent propellant tanks. And the U.S. has been a leader in, the U.S. is a leader in vulnerability in space. So we have more assets, more target area, more dollars invested than anybody else. So we are also, very deservedly, a leader in raising people's consciousness about the things, about doing things like not leaving things in long-lived orbits. The 25-year rule is propagating over the world. Venting propellant tanks, draining batteries, all that stuff is becoming, all the easy stuff to reduce the future growth in debris is being taken by nearly all spacefaring nations.
And just so we're all on the same page in terminology, that's all broadly called mitigation.
Mitigation, that's not removal. All it does is reduce the rate at which the problem is getting worse, okay? And until February 9th or so of last year, the contribution of car-car collisions had been overlooked. It's still overlooked in some places. We worry about hubcap car collisions because there are more hubcaps. But it turns out that because car-car collisions, there's far more collision cross-sectional area, they are likely to be nearly as common as hubcap car collisions, and they're likely to involve, as with the Iridium Cosmos, 300 times more energy per unit mass than a hubcap car.
And that was the crash you just referenced that happened last year.
Right, and there are 2,500 known pieces of debris from that, approximately.
Bob, why don't you get us started with the microphone? And I'll also remind you, if you want to ask questions as we go along, please feel free to put up your hand, but I won't call on you unless you use a mic.
First, let me say that you're probably going to get the feeling that you've walked in the middle of a conversation, and that's exactly what's happened. Over the last 18 months to 2 years, a group of about 100 people scattered around have been really thinking through the implications of what's been happening in orbital debris. And there are historic reasons why the conversation started when it started, but once it got started, it developed a life of its own. And the Space Frontier Foundation and foundationers have been very involved in that discussion. We've been, doing papers and talking to people, and it's been very much a part of the Foundation's job to change the conversation about space. And over the last 18 months or so, we've pretty dramatically changed the conversation about orbital debris. And one of the things we've learned is that there are some similarities between orbital debris and NEOs, and there's some differences, and we're going to talk about that. The Foundation is particularly interested in this because what we want to do is to use the nearly unlimited resources of the solar system to make life better for everybody, to protect Earth's fragile biosphere and to create a freer and more prosperous life for each future generation. I mean, that's what we're about. And so orbital debris and NEOs are both very critical to that part of our vision. And so when this discussion started, we just sort of dove in, and I think you'll find that it's a very good example of how the frontier philosophy impacts on this discussion, because the other people involved in this don't share our vision. I mean, in debris, a lot of the people concerned in the military, their interests are not in using the orbital debris.
What became orbital debris. Surprisingly, the real orbital debris collision issue, you have to have two spacecraft in orbit at the same time. The Russian second launch, I think, occurred after the first one a decade, so they didn't cause the problem. If you look at the list of old objects in space, I think 96 out of the 100 oldest are U.S. The U.S. pioneered the use of high, long-lived orbits. So, but I don't want to blame the U.S. Every country active in space has done some things that they would later regret, okay? In 1963, we did the Project Westward. We put 480 million needles this long in high orbit. Adlai Stevenson actually argued in the UN that they would re-enter within 3 years, and most of them did, but we don't know how many are still up there, okay? But every country has done things that in later thought were, gee, I wish we hadn't done that, but we can't admit that publicly, okay? If you look at the size versus frequency distribution for near-Earth objects, it's kind of a straight line and log-log curve, very slight curvature. That's not true for debris. There are actually three distinct bumps, okay? The first bump is intact spacecraft. And we think of CubeSats and, regional satellites, but the typical intact satellite weighs about a ton. And you could regard the intact satellites as being mostly cars. The results of explosions and collisions could be regarded as hubcaps. They tend to be under 5 pounds, but trackable. But besides the hubcaps, there's also what I call bullets, the objects that are untrackably small. They can be detected by use of the Goldstone radar, but limitations of that radar only allow you to get statistical data. They don't allow you to establish orbit. So we know that there are a lot more small bullets up there than there are hubcaps, but we can't dodge them, okay? And one of the bad stories about space station that you don't hear is that for every object that the ISS maneuvers to avoid the possibility of a collision with, there are about 50 objects which we don't track, which are large enough to put a hole.
Interested in just getting it out of the way so it doesn't cause them any problems. A lot of the people involved in NEO discussion are scientists, and they couldn't care less if we characterize them for, in terms of their utility for a future civilization. They want to know where they came from billions of years ago. And okay, with this, and we've kind of been trying to bring all the various parts of the discussion together and to get everybody focused on how do we do this in a way that is frontier enabling, to use our term. We don't always use that term when we're talking with the rest of the community. And all of the 5 of us plus several other foundationers have been engaged in that debate and are going to stay engaged in that debate. And this is a work in progress.
And thanks, Bob. And I just want to also submit that this, to me, is a really good, this is almost like a case method in business school, except that what we're applying is really the Foundation's approach. And it's an approach that is inherently multidisciplinary. And when you look at this panel, you see a lot of technical expertise, but also a broader expertise. And that's really only a small part of what's involved in this debate. So I want to start by just having Joe and Dennis and AC really kind of lay the groundwork for us in describing what it is we're talking about. And I want to start by taking the low road on debris and then working our way up. So I want to start with Joe giving us some background about the debris threat at low Earth orbits at LEO, and then move into talking with Dennis about geostationary orbits, and then AC is going to really kind of take it home and talking about NEOs, and then we'll start to unpack the pieces here. But at each step of the way, the goal here is to talk, as Bob is saying, both about opportunity and threat, and how to make threats turn into opportunities for NewSpace and for commercial development. So, Joe, why don't you get us started on LEO?
Yeah. Orbital debris, man-made orbital debris did not exist until Russia launched the first satellite, and then battery died. Okay, then
The talk will be moderated by Baron Zoka, and he is a Foundation board member, former chair, and a senior fellow at the Progress and Freedom Foundation. Baron?
And you forgot to mention, I'm also one of those lawyer varmints. So I'm not a subject matter expert, and my purpose here is really to bring you, the people who really know what they're talking about, so they can talk about the technical business and then eventually policy issues that I think might tie together to some extent the topics that we have today. So I'll just briefly introduce our panel, and then I will show you a roadmap we have for our conversation, because we really want to engage the audience as we go along, but I want you to see where we're going so you don't skip ahead of the rough outline we have. So you probably all know Bob Werb, who's our current chairman. Dennis Wingo has been a real leader in the space business, very focused, I would say, perhaps more than anybody, on the immediate business realities and opportunities in the space industry. And as Dennis will always remind you, we have a $200+ billion a year space industry today, and it's ComSats and other satellites, which is actually directly relevant to our topic today. Joe Carroll is famous for having not much to say about anything, but knowing a hell of a lot about a lot of things, in particular tethers and orbital debris, and how you would actually go about mitigating and removing orbital debris. And then to my left, AC Trania is also a Foundation board member and has been very active for a long time on NEOs, and is, I dare say, just as focused in some ways as Dennis is on the business realities. So that's really where I wanted to start here. And if we go to the next slide, I'll show you, if you go through the slides about each of the panelists, which might have been helpful when I was introducing them. There's a slide that just kind of lays out the roadmap. So where we wanted to start before getting into substance was really about the vision here. So why it is that we should care and why this relates to the Foundation's mission. So